This is my attempt to produce a self-paced worksheet. This worksheet is 23 redox and electrode potentials with exam-style questions. Read the question, pause the video, see if you can answer a question, then push play to see if you have got the correct answer. So standard electrode potential. What is the standard electrode potential of a half cell? This is the voltage of a half cell when it's connected to a standard hydrogen electrode. And then obviously we need to state the standard conditions. So pressure of 100 kilopascals, which is also the same as 1 bar. A temperature of 298 Kelvin, which is 25 degrees centigrade. And all solutions having a concentration of 1 mole per decimeter cubed. The second question is, what is a reducing agent? A reducing agent is something which is going to add electrons to whatever's being reduced, or the alternative definition is a species which is oxidized in a redox reaction. Next thing is, what is a fuel cell? A fuel cell is a cell which uses the energy from a reaction of a fuel with oxygen to create voltage. Here is a reaction between sulfur dioxide and bromine. Give a change in your oxidation state for both sulfur and bromine. Oxygen is always -2, unless of course it's a peroxide or combined with fluorine. So this means the sulfur, as there's two oxygens with an oxidation state of -2, sulfur must be +4. On the right, it's forming SO4 2-. So there are 4 oxygens, each with an oxidation state of -2, and that -8 plus whatever sulfur is must give us 2-. So sulfur here must now be +6. Bromine goes from 0 to a bromide ion, so Br-, so it's gone to -1. If we think about the equation, it's got 2 bromide ions, so there has been a gain of 1 electron per bromine. So total number of electrons gained by bromine going from bromine to bromide is 2, which fits with sulfur going from +4 to +2. So sulfur is obviously losing 2. Next question is, use your answer to part I. So as he's using part I, this cannot be answered in terms of electrons, but must be answered in terms of oxidation numbers. So again, bromine or Br2, you couldn't just write Br, and I'm going to sort the format out in a second. And the reason is because the oxidation number decreases, and so it is reduced. The other way to think about it is, what is oxidized? Sulfur is oxidized, so whatever else is present in the reaction which is changing oxidation number must be the oxidizing agent. Hydrogen sulfide gas is a reducing agent, and an acidified solution of manganate 7 ions acts as an oxidizing agent. Here are 2 half equations. Explain how half equation 1 shows that hydrogen sulfide is a reducing agent. So if we look at the equation, we could write the oxidation numbers behind or underneath the formulae. So hydrogen is +1, sulfur is -2, and here on the right, sulfur is now 0. So the oxidation number of sulfur has increased from -2 to 0. We can say it has been oxidized. So to balance the 2 equations, we need to get rid of electrons. So we take both equations and we try to get the same number of electrons in each equation. The first equation would be multiply everything by 5, so we can get rid of the electrons by timesing everything by 5, so we have 10 electrons. If we multiply the second equation by 2, this will give us 10 electrons in the second equation, like so. Giving this, and we can now combine these 2 equations. So putting everything on each of the equations left sides together, and on the right we're putting everything there also together. We can see there are 5 electrons on both sides of the equation, so the 10 electrons for both equations can disappear, and we now have our balanced equation. We can scroll down and read about a titration experiment. So I might just highlight some key things. So we start off with 25 centimeters cubed of dichromate solution, acidified, treated with excess, so maybe this might be important, potassium iodide solution. The iodine produced was titrated with a solution of sodium thiosulfate, and the concentration was given. We've got two equations here, and we might look at the link between them. So the final bit of the titration was the sodium thiosulfate with iodine. And if you think about the equation, it's got a ratio of 1 iodine molecule to 2 thiosulfates. And here, we've got a link between 3 iodines and 1 potassium dichromate, like so. So we're going to use this in a little bit. So explain how you would carry out a titration to find the amount of iodine present in the sample after treating with potassium iodide. So some of the key things is thinking about the piece of equipment, visualizing it, and thinking about what you'd do. Obviously, what are we putting in the different pieces of equipment, and how are we going to be measuring? So we'd obviously use a burette for the sodium thiosulfate because we're adding the sodium thiosulfate. Place a conical flask containing iodine below, and we'll add the thiosulfate to the iodine vessel and slow it down near the end and do it drop by drop. We would obviously probably have carried out a rangefinder titration first. Obviously, if we're getting rid of iodine, at the end of the experiment will be no iodine present. So we detect when there is no iodine present using a starch indicator, and at the end it will go from blue-black to colorless. So we need to find out the concentration of the potassium dichromate. If we go slightly back up, I might just do the calculations up here because this will make life easier. We have a concentration and the volume for thiosulfate, so we could obviously do the volume, divide by 1,000, times by the concentration, times 0.1, giving us 2.44 times 10 to the minus 3. And let's write this moles of thiosulfate. So if we now look at the equation, for every 2 moles of thiosulfate, 1 mole of iodine would have reacted. So we could obviously take this value and divide it by 2. And this will give us 1.22 times 10 to the minus 3 moles of iodine. The next thing we could obviously do is we've got 3 moles of iodine, and this was formed in the reaction where we only had 1 mole of potassium dichromate. So we're going to divide this value yet again by 3 to get our number of moles of potassium dichromate. So divide this value from a previous line by 3, giving us moles of potassium or dichromate. It tells us the original volume it was in. It was in 25 centimeters cubed. So we're going to have to obviously take this value and work out concentration. Concentration is obviously moles over volume. So to do this calculation, I obviously haven't divided it by 3 just yet. Divide by 3 gives us 4.07 times 10 to the minus 4 moles of that. So we'll do concentration is equal to moles divided by a volume. Obviously we need to have it in 25 centimeters cubed in decimeters cubed. So divided by 25 over 1,000, giving us 1.63 times 10 to minus 2 moles per decimeter cubed. Now, units were grams per decimeter cubed, so we need to work out what mass of 1 mole of potassium dichromate. So it's going to be equal to, get hold of the periodic table. So potassium is 39.1, so 39.1 times 2 plus chromium times 2, so 52 times 2 plus oxygen 16 times 7 gives us a mass of 294.2, and that is, let's put a label in, MR of potassium dichromate. So if we think about it, as in terms of standard units, this would be equal to grams per mole. And this means if we take a concentration in moles per decimeter cubed, that would mean we have that many moles per decimeter cubed. And if we had 1 mole, it would have a mass of 294.2. Instead, we've only got 1.63 times 10 to minus 2, so we're going to multiply these two numbers together to give our final answer times 294.2, giving us a final answer for 4.79. So we can move on to the next question. Iron 2 sulfate exists as a hydrated salt. And what we need to do is, or students look at different methods to find the value of X. One is using a titration method, one is using only a measurement of mass. In the titration method, a certain mass of iron 2 sulfate was dissolved, made up to 250 centimeters cubed, and then, this is a key bit, 25 centimeters cubed of that solution was removed. So we're going to have at some point a divide or times by 10 bit there. This 25 centimeters cubed was titrated against a 0.02 molar solution of potassium dichromate solution, and the volume required of potassium manganate was 13.6. Now, iron 2 ions, you may or may not know this, give solutions a very pale sort of yellow colour. But the key bit is, if you're adding potassium manganate solution, at some point the potassium manganate will not be converted into Mn2 plus ions, which are colourless, but they will exist. So it will go, the first bit's in brackets because we obviously don't need to necessarily know that, from pale, let's go from very pale yellow to the colour of potassium manganate, so and pink, pale pink colour. Why do we need to use sulfuric acid? If we write the equation down for the use of potassium manganate, it will become clear. So if we write our equation down, MnO4 minus, the manganate ion, and we need to convert it, and it reacts and forms Mn2 plus. Now, obviously need to think about how to balance this equation. Where does the oxygen go? That goes into water, so H2O. There are 4 oxygens on the left, so we'll need 4 oxygens on the right, so plus 4 H2O. As we've got 4 H2Os, that means we'll be 8 H pluses on the left-hand side to balance it out. And then if we think about the next bit, manganese has gone from manganese 7 to manganese an oxidation state of +2, so it is going to be plus 5 electrons. So this is our equation. So you can see why is sulfuric acid necessary, and it's necessary to provide the H plus for reduction of manganate ions. So calculating the value of x. I'm going to do all of this up here because it's going to be easier. So firstly, we could obviously work out the number of moles of manganate ions used in this experiment. So moles is concentration times volume, so 13.60 over 1,000 times by 0.02 gives us a value of 2.72 times 10 to the minus 4. Let's just put this in words, moles of K or MnO or minus. So we now need to work out how many moles of iron 2 plus ions, and we'll need to write an equation down, working out the ratio between the manganate ions and the iron 2 plus. Now, tells us that obviously it's going from iron 2 plus ions. The other common oxidation state of iron is iron 3 plus, so it's going to go from Fe2 plus going to Fe3 plus the loss of 1 electron. So we have these two equations which we'll need to combine. And you should be able to just see they go together quite nicely. We'll just have to multiply this first equation by 5, like so. And then if we add the two equations together, we'll get plus 5 Fe2 plus on the left and plus 5 Fe3 plus on the right. So we have worked out the number of moles of manganate iron. So the number of moles of iron 2 plus there's a ratio of 1 manganate 7 iron to 5 moles of iron 3 plus. So we're going to have to times this value, which we've just calculated, by 5. So 5 times that, giving us a value of 0.00136 moles of Fe2 plus. And we could just be extra careful here and say that is in 25 centimeters cubed of solution, because sometimes people forget to multiply by 10. Remember, we took a 25 centimeter cubed sample from a 250. So next stage is we're going to take the value for what's in 25 centimeters cubed and times it by 10. So 10 times the amount in 25 centimeters cubed gives us a value of this 4 moles in 250 centimeters cubed. So now we've got number of moles, we know the mass, so you could also remember moles equals mass over mR. So this means mR is equal to mass over moles. So we've got a mass of 3.79, which is the text highlighted above in green, divided by the number of moles, so 0.0136, giving us the number of moles of a hydrated iron compound is 278.7. This mass is made up of iron sulfate plus water. So if we take the mass of the hydrated compound and we take away the mass of iron sulfate, so iron sulfate is 55, so iron is 55, its molar mass, plus sulfur 32.1 plus 16 times 4. This will give us the mass of water which is present. So now we need to work out how many moles of water is present. So moles equals mass over mR. So we've got mass of 126.8 divided by the mass of molar mass of water, which is 18, giving us a value of 7.05, giving us a value of x is equal to 7. So we've got that question done. So the second one is, how could you work out the mass of water by using a change in mass method? If you think about it, when you heat most compounds, they will the first thing it will do is lose the water. So it's going to be the idea of heating it, causing it to lose mass, and then seeing what the change is. So stage one will be weigh crucible and record mass, weigh crucible with hydrated salt and record mass, weigh crucible, heat crucible and salt to drive off water and until constant mass is obtained, and then leave to cool, then weigh crucible with anhydrous, meaning the salt without water. And obviously we could, it doesn't say that we need to sort of talk about calculation, but obviously you could talk about the idea, obviously calculating the difference between the crucible and then crucible and salt to find out the mass of salt present. And then you can also talk about calculating the mass of anhydrous salt by taking the mass of a crucible. Oh, sorry, the last one you could actually just do is compare crucible width hydrated versus crucible width anhydrous salt, just to calculate the amount. In terms of amount, I mean mass of water present. So we now move on to a redox question. A student who is investigating redox of vanadium wants to carry out an experiment to measure the standard electrode potential of a half cell based on the redox system below. Complete this diagram to show details of the cell the student would set up, include details of all substances and their concentration and conditions required. So what we need to do is draw another beaker on the right hand side. We need to have a wire, and we need to make sure it's joined. We need to say what this is, and this is going to be platinum, so PT for platinum. Then we've got our solution, and it's got vanadium 2 plus vanadium 3 plus ions, so V2 plus AQ, V3 plus AQ. That was terrible writing, sorry about that. And then you could also say both solutions 1 mole per dm minus 3. And then we need to make sure we've got a salt bridge. We could label that salt bridge. And also we need a high resistance voltmeter, so a V there. Obviously try to not have a line going through the circle. So what else is missing? We've got the hydrogen gas. We obviously need to make sure what pressure it's at, and we could do at 100 kilopascals of pressure. H plus ions, we need to state the concentration, so 1 mole per dm cubed for the hydrogen ion concentration. And obviously one final thing to mention is the temperature of 298 Kelvin. So I think I have got everything there which I need. So hopefully that's good. Students finds that the electrode potential of a V3 plus to V2 plus half cell or has a value of minus 0.26. It says in the question that this is combined with a VO2 plus 2H plus E minus goes to V3 plus H2O half cell. It says here that the V3 plus V2 plus half cell is a negative electron, so that's one providing electrons. So let's just get to the next little bit. So if this is a negative half cell, that means that this one's providing electrons. So the bottom one is going to the left, and the top one is going to the right. So when we combine the two half cells, the E standard value will be equal to the one for V3 plus V2 plus reverse, so minus 0.26 plus the mystery one, and it says that the total voltage will be equal to 0.6 volts. 0.6 volts. So if we work out what the mystery number must be, minus minus gives us a plus value for that. And then if we take away 0.26 from both sides, the unknown voltage must be 0.34 volts. So that's saying that the voltage for this half cell here is 0.34 volts. So we've got that one now solved, and we can write the value for that particular half cell there. Student finds when they mix VO2 plus with V2 plus, a chemical reaction occurs. Is this consistent with a standard electrode data? The more positive one will go to the right, the more negative one will go to the left. So yes, because the VO2 plus / V3 plus system has a more positive E standard than the V2 plus or V3 plus. So VO2 plus acts as a oxidizing agent and oxidizes V2 plus to V3 plus. So there we go. To write an equation, they've both got one electron in, so that makes life very easy in terms of combining the two equations. We've said this one at the top is just going to the right, so we can just copy that here. Well, bottom one is going to the left, so we could just put the species from the bottom into the equation, get rid of the electrons, or just get rid of the electrons as one in each case. That obviously is supposed to be aqueous. There's some interesting fonts in this document, is all I can say here. And then on the right hand side, we need V3 plus, so we put that in there. A student then tries to add some solid tin to a solution of vanadium 3+. She predicts that a reaction should occur. So solid tin, so she's suggesting the top equation, which I just wrote down, is going to the left, like so, and the bottom equation is going to the right. So if this is the case, the one which goes to the left is going to be the more negative one. So that's what it's suggesting. The SN2 plus 2 electrons goes to SN tin is more negative. So if we just did pretend values of minus 0.6, for example, volts, when we would combine the two equations, we would do E equals, well, more negative one is swapped around, so it would be 0.6 minus 0.26 volts. So, but unfortunately this reaction didn't occur, so why would this be? Again, we've got to remember what standard conditions are, so maybe concentration of ions may not be 1 mole per dm cubed, which is quite likely in most cases. Other things might be, it could also have a very high activation energy, so there might be some reason why it would only work if we actually gave it some sort of energy or catalyst to actually help speed up the reaction. Again, maybe temperature technically you could mention, but I don't think it's probably likely to be the important one. But if you can't think of something else, it's well worth mentioning.